In the 1960s, the primary objective of lunar exploration was survival. Success meant landing a spacecraft, stepping outside, and making it back home without a technical failure. To ensure that survival, the Apollo Site Selection Board followed a rigid set of safety criteria. They needed equatorial plains that were essentially lunar parking lots, flat expanses with slopes of less than 2 degrees, clear of large boulders or deep craters. Orbital mechanics added another constraint: the free return trajectory. Every early landing site had to sit along a path that would naturally loop the spacecraft around the moon and coast it back to Earth if an engine failed mid-transit. But the safety of these equatorial plains makes long-term habitation nearly impossible. The lunar night lasts for 14 Earth days, bringing catastrophic temperature swings. A flat landing site goes from a boiling 127 degrees Celsius in the sun to negative 173 degrees in the pitch black. These regions are also bone dry. There is no native water available to sustain a crew or manufacture the propellant needed to leave the surface again. A 3-day mission works perfectly in the flatlands, but to build a permanent settlement, humanity must abandon the safe zones and target the most extreme and treacherous geography on the moon. The new primary target zone for modern space agencies is the rugged, mountainous terrain of the lunar South Pole, specifically the Shackleton-Digger-Losh Ridge. The strategic value of this ridge is a result of the moon's axial tilt. While Earth tilts at 23.5 degrees, the moon sits at a mere 1.5 degrees relative to the sun's rays. Because the moon stands almost perfectly straight, the sun always sits on the horizon at the poles. High mountain ridges catch this light nearly 94% of the year, offering an almost unbroken supply of solar power. However, that same low lighting angle creates the opposite effect just a few hundred meters away. The deep crater floors adjacent to these peaks are cast in permanent shadow, creating zones that haven't seen sunlight in billions of years. These permanently shadowed regions are deep freeze traps sitting at negative 415 degrees Fahrenheit. This is where we find ancient water ice, the essential resource for drinking water and manufacturing liquid rocket fuel. Operating here is an immense challenge. Landers must perform pinpoint touchdowns on narrow, sunlit ridges while navigating long, disorienting shadows and a fluffy regolith that is more porous and unstable than the dust found at the equator. The South Pole is a landscape of volatile trade-offs. The layout of the terrain forces astronauts to live on the narrow boundary between infinite solar energy and deep freeze water reservoirs. While the poles provide resources, they offer very little shelter. For long-term protection, geologists are looking back toward the equator, specifically at Mare Tranquillitatis and the Marius Hills. High-resolution mapping has identified LUA, lunar skylights, that act as entries to massive subsurface caves. These are ancient, hollow lava tubes formed by volcanic activity. On the surface, human biology is under constant threat. Without a thick atmosphere or magnetic field, astronauts are exposed to unshielded cosmic radiation and a relentless rain of micrometeorites. These lava tubes provide a natural solution. They offer massive internal volumes and hundreds of feet of solid rock shielding, maintaining a stable, insulated temperature of roughly 20 degrees Celsius. While the poles provide the raw materials for industry, these subterranean vaults provide the only geographically stable sanctuaries capable of protecting human life for decades. The moon is a complex continent of highly specialized geographic provinces. This includes the far side, where the Daedalus crater serves as a unique astronomical sanctuary. It is the only place in the solar system shielded from the electronic noise of human civilization. Space agencies are already coordinating to exploit these specific nodes. The International Lunar Research Station, or ILRS, is a collaborative framework designed to finalize site selection and verify the technologies needed for high-precision soft landings. NASA's Artemis program is physically building the infrastructure, like the Space Launch System, required to reach these exact coordinates. The SLS is a super heavy lift rocket designed specifically to deliver the mass needed for long-term lunar outposts. No single coordinate on the moon provides optimal power, water, and shelter simultaneously. Success requires an integrated supply chain, mining ice at the poles, sheltering in equatorial lava tubes, and observing from the far side. Only by claiming these extremes can we shift from temporary visitors into permanent residents.